Question 6 from the 2025 Higher Physics Paper 1. A ball of mass 0.164 kilograms is dropped from rest and falls towards the ground. The ball collides with the ground and rebounds upwards. The speed of the ball just before it hits the ground is 4.85 metres per second, and the ball is in contact with the ground for 0.180 seconds. The speed of the ball immediately after it rebounds from the ground is 3.96 metres per second, and we've got to calculate the mean force exerted by the ball on the ground during the collision. And we're given those 5 responses. Well, this is going to be a change of momentum problem, and we know a change of momentum problem leads to an impulse. Whenever there's a change of momentum, there's going to be an impulse, and we're given the contact time, so therefore we can go ahead and work out what the mean force is. So first of all, we have to take into consideration the directions of the momentum. Downwards is going to be negative, because remember, momentum is a vector. So the momentum before, P equals mu, is easily calculated, and this time it's going to be 0.64. and you have to multiply it by minus 4.85. Remember, the velocity down the way is negative. So we multiply that out, we get an answer of minus 0.7954 if you do that in your calculator. Units for momentum are kilograms ms minus 1. Now, the momentum afterwards, after it collides with the ground, is going to be mv, and we're going to have the same mass, 0.64, multiplied by, this time, 3.96. And remember, the velocity is upwards, and we take the velocity to be positive. So we work out that momentum, we get an answer 0.6 and 494 kilograms meters per second, and we'll keep all those figures in at the moment till we get to our final answer. Now you can see we're going to have a change in momentum. So the change in momentum is going to be delta P, which we know is going to equal to mv minus mu. And we can find the change of momentum, that's going to be equal to the impulse. So the change of momentum is momentum afterwards, which is 0.6494. Take away a minus, and it's going to be 0.795. That's the most important part in this problem, 0.7954. So we do that in our calculator. Remember, it's a minus. Take away a minus, going to give you a plus. We have the change of momentum equal to 1.448. So the change of momentum is 1.448, and it'll be kilogram meters per second. Now we know that the change of momentum is exactly equal to the impulse. So the impulse, Ft, equals the change of momentum, mv minus mu. So therefore we have the impulse, therefore impulse Ft is going to be equal to 1.448, and we change units to newton seconds. Remember, change of momentum is kilogram meters per second, impulse is newton seconds. Now we have the contact time. The contact time is 0.18 seconds, so therefore F times 0.180 is going to equal to 1.448, and therefore we can just say that the average force F, or the mean force, is going to be 1.448 divided by the contact time, 0.180. And we do that on my calculator, we get a mean force of 8.03 newtons. And that gives us the following answer. If I can go up and see this, it's going to be answer E. So we're going to have answer E for question 6. Question 7. Two samples of modelling clay X and Y have the same shape and mass. Sample X is made of a softer clay than sample Y. The samples are both released from the same height and fall towards the ground. Both samples come to rest when they collide with the ground. And a student makes the following statements about the samples colliding with the ground. Statement 1 is sample X comes to rest in less time than sample Y. Statement 2, the mean force exerted by the ground on sample X is less than the mean force exerted by the ground on sample Y. And the third statement is a change in momentum of sample X is less than the change in momentum of sample Y. Well, let's summarise what's happening by taking a look at this diagram. There's the two masses there, and we know that mass X, the sample X of the clay, that's going to be the softer one. That's going to be the soft one there, and this is going to be the harder one. So that's us got the two types of material. Now, they're going to both fall from the same height, which means they're going to have the same velocity just before they strike the ground. So they're going to have the same velocity v just before they strike the ground, which means they're going to have the same change of momentum because they're going to come to rest. Therefore, both x and y have got the same change of momentum. So same change of momentum for both of them, because both are going to have the same velocity, and therefore when they come to rest they're going to have the same change of momentum. So we can rule this one out here. The change of momentum of sample x is less than the change of momentum of sample y. That's obviously wrong, because because they hit the ground at the same time and are brought to rest, will have the same change of momentum. Now, what else can we say? Well, we know that the softer material is going to have a change of time, a time of contact, which is going to be a lot longer. So that's going to be a lot longer. Change of time there is going to be a lot longer. And that means if we look at the impulse, so the change of momentum is going to be the same, we're going to be looking at this idea of the impulse, F delta t. So it says sample x comes to rest in less time than sample y. Well, if the sample x is made of softer material, it will come to rest in a longer time. So we can rule that one out as well. So that one is wrong. What about the second statement? The mean force exerted by the ground on sample x is less than the mean force exerted by the ground on sample y. We know that F delta t is the change of momentum. We know the change of momentum is going to be exactly the same. So F delta t is going to be p, but the time of contact is going to be a lot less for material y. So therefore, when we work out the average force, F equals p over delta t, we know that the one with the longer time of contact will be the less force exerted by the ground. So the mean force exerted by the ground in sample x is less than the mean force exerted by sample y, and that's true because if sample x is going to take a longer time, then the mean force is going to be bigger. A longer time means a bigger number in the bottom, same change of momentum, therefore the force is going to be smaller. So the mean force exerted by the ground on sample x is less than the mean force exerted, and that's going to be true for that one there. So we've only got one answer, and that's going to be 2, and it looks like the answer is going to be B. Question 8. The Large Hadron Collider LHC is contained in a circular tunnel. A technician working at the LHC measures the length of the tunnel to be 26.7 kilometres. Protons in the tunnel are accelerated to a speed of 0.999 c. And the length of the tunnel in the frame of reference of protons is, and you get the 5 responses. This can be a little bit tricky problem here, so we've got to get our facts right of who is what and what is where in what reference frame. Well, what we know of is that the proton is flying past the tunnel. So we can think of the proton like that, and the proton is flying past the tunnel. But we can think of the tunnel as flying past the proton. So we can draw the tunnel like that, and the tunnel is flying past in this direction here. So there's a tunnel flying past there with a speed of v equal to 0.99 c. So v is going to go to 0.999 c. So we think of the proton at rest in its reference frame, and the observer, which is on the Earth, that's a technician, he's going to measure the length of this tunnel in his reference frame to be 26.7 kilometres. Now that will be the proper length of the tunnel. So we're looking for the relativistic length according to the proton. And we know the equation. The equation is the relativistic length L prime is going to go to the proper length of the tunnel measured in the reference frame, which is at rest, that's the technician's reference frame, times the square root of 1 minus v upon c and all squared. So we know that L prime, the relativistic length of the tunnel, according to the reference frame of the proton, is going to equal to 26.7 kilometres multiplied by 1 minus, and we've got 0.999 c, and we can see if we put 0.999 c and divide it by c and all square that, we're going to have the following. We have 26.7 times the square root of 1 minus 0.999, and it's going to be all squared. Now if we do that in our calculator, we end up with the length, the relativistic length as seen by the proton, to be of the value of 1.19 kilometres. And that will be the length of the tunnel as experienced by the proton. So the answer to that is going to be the following response. It's going to be B. Question 9. A student makes the following statements about cosmic microwave background radiation. Cosmic microwave background radiation provides evidence for the Big Bang Theory. Statement 2. Cosmic microwave background radiation reaches the Earth from all directions. And Statement 3. Measurements of the peak wavelength of cosmic microwave background radiation indicate that the average temperature of the universe was lower in the past than it is now. Let's take a look at the picture, the famous picture of the background radiation, and now you can see it there. So cosmic background radiation provides evidence of the Big Bang Theory, and that statement 1 is correct. So we'll mark that correct there. Statement 1 is correct. Microwave background radiation reaches Earth from all directions. Well, this is true, as you can see from the picture. This is a 360-degree picture of all the universe, and you can see the cosmic background radiation coming from all directions. So that is correct as well. Measurements of the peak wavelength of cosmic microwave background radiation indicates that the average temperature of the universe was lower in the past than it is now. And that's false, because the temperature was highest in the past. The prediction of the Big Bang Theory predicts that the the temperature of the universe should be about 3 Kelvin, and when we analysed this picture here, we found out that the temperature was 3K, so it agreed with the theory of the Big Bang. So we have statement 1 and we have statement 2 correct, and statement 3 is false. So 1 and 2 only, and the answer is C. Question 10. A potential difference of 1.2 kilovolts is applied across 2 parallel metal plates in a vacuum. An electron is released from rest at the negative plate as shown, and the speed of the electron just before it reaches the positive plate is, and we'll get 5 possible responses. We know for a fact that when the electron is placed in the electric field is going to do work on that electron, and the work is given by the following statement: work equals the charge on the electron times the potential difference which the electron has passed through. Now that work done is going to be transferred into kinetic energy, so we have that being transferred into kinetic energy, EK. And we know what EK is equal to. It's 1/2 mv squared. Remember, small v is the speed of the electron. Now if we equate those two things together, 1/2 mv squared is going to equal to qv, then we can rearrange to find out what v is. And we do that as following. We can say mv squared is equal to 2qv, or 2 times the work done by the electric field. V squared is going to equal to 2qv over m, and m is the mass of the electron, and finally v will be equal to the square root of twice the work done, which is qv. Q is the charge on the electron, v is the potential difference, divided by the mass. So all we have to do is put in the numbers for that. Then we have the square root of 2 times the charge on the electron is 1.6 times 10 to the minus 19 coulombs, multiplied by the potential difference it goes through. In this case, it's going to be 1.2 kilovolts, so it's going to be 1.2 times 10 to the power 3, and we divide that all by the mass of the electron, which you can find in the relationship sheet. It's going to be 9.11 times 10 to the minus 31. So that's, you've done all the hard work. All it needs to do is just do it simply with your calculator, and you end up with a value of the speed to be 2.05 times 10 to the plus 7 meters per second. We can rearrange that to give us, not rearrange it, we can use significant figures to give us 2.1 to 2 significant figures times 10 to the power 7 meters per second to 2 significant figures. So the answer we're looking for in this case, 2.1 times 10 to the power 7, is going to give us answer C.